Chapter 5 is a relatively small chapter because all it's covering is the physical analysis. Physical analysis of urine doesn't take very long, and it's just, for the most part, it's going to be visual. These are your objectives. Please go back and study them. And these are your key terms. If you don't know what they are, please look them up. We will use them. When we start talking about color, those have to do with the Euro definitions down at the bottom. I do talk about them, but I don't go into a whole lot of detail, and it's not on the slide, so I would suggest looking the words up. The other ones should be pretty familiar. When you perform a physical examination, these are the 4 things you're looking for: color, clarity, specific gravity, and odor. Whenever you are trying to determine the color and the clarity, you first have to transfer it into a clear labeled secondary tube. Then you can look at it. Don't use the original container that it comes in. It can make the color look different than what it really is, so you always have to pour it off before you document your color and clarity. These are normal colors, and this is how you will report them in our labs. Normal urine is yellow, and the intensity of the color is going to be related to the concentration. When you have a dilute urine, it's usually going to be pale or yellow or straw colored. So those are kind of the first 2. And then when it's more concentrated, it can become a dark yellow. A lot of times when you have a first morning specimen, those are the ones that are going to be darker because they're more concentrated. Remember, we talk about different collection methods. So first morning is always going to be darker, and that's the one that is the 3rd tube. A lot of times also when you drink a lot of water, that also can make your urine more of a light pale color, like the first one, straw, or sometimes it's even almost clear, and looks like water. Your amber color, it's a little harder to determine what it looks like on the screen, but amber colored urine looks a lot like tea. If you look at table 5.1 in your book, it shows you laboratory correlation of urine color and gives you some abnormal colors in your book also. Abnormal colors can be indicators of a pathological condition, or they can also be from different medications that a person may be taking. Remember the 3 Euro definitions that I gave you to look at. Urochrome is normal metabolism, which is going to be a yellow color. Urobilin is when we have hemoglobin degradation, and it will cause an orangish to brown color. And uroerythrin is due to melatonin metabolism, and that's going to cause something that's a pink color, and that's attaching to the urates. So some of these will come back when you do your chemical testing, and you'll need to know them again. Clarity is what we're talking about, the transparency of the urine. Can we see through it? These are the 4 that you use: clear, hazy, cloudy, and turbid. When you have a clear specimen, there's no visible matter. A hazy specimen has visible matter, but you can still read through. And then hazy is going to be the one that's just slightly cloudy. Okay, so that's hazy. They call it a little different in your book than what we talk about in lab. Cloudy is going to be blurred, but you can still see the print. In turbid, you cannot see through the urine, and you also cannot see the print. So if you're not real sure about the clarity of the specimen that you have, you can always hold it up to one of the pieces of paper we have and determine it based on looking at that. And can you see the words on the other side? So that's a lot easier than trying to just look at it and guess. So hold up a piece of paper behind it, and you'll be able to see that a lot better. Your normal urine should be clear. You should be able to see through it just fine. Sometimes, though, you can also have a normal urine that has substances like epithelial cells in it, and then that can increase the turbidity. And to avoid that, like especially if a patient's going to do a clean catch midstream urine collection, they need to make sure that they're given clear instructions about how to properly collect it. because remember that's the one we want to use a lot more for doing a microscope, or not a microscopic, but doing microbiology testing. It's going to be the clean catch midstream. So that's definitely why it's going to be a better collection, because they have the instructions for cleaning, and you need to go back and read that too. You need to know how to collect your specimens, and that was in the previous chapter. Specific gravity is where we're talking about solute concentration. Your solute concentration is looking at the dissolved substances. Specific gravity is a good test to do, because what it's testing for is renal function and hydration. And then it's also helpful in determining whether or not your specimen is water, or if it is detecting some type of a contamination based on those results. So if it's very decreased, then we would look at it and be like, okay, well, is this water? Water is 1.000. So if it's below that 1.002, then you may have a specimen that's water, and you'll have to test it. If you have something that's above 1.035, then you could possibly have some type of a contamination. Now, glucose and protein will elevate your specific gravity, but not by a whole lot. But just so you know, it can cause an elevation. So if they were present, especially if they're present in a large amount, then it's going to affect the specific gravity. These are the different ways that you can measure specific gravity. So your indirect methods of refractometry and reagent strips, I'm going to talk about both of them a little bit, and then give you kind of a comparison of the two. So when you use a refractometer, it's an indirect measurement of specific gravity. What it's doing is measuring the velocity of light in the air versus the velocity of the light in the solution. The concentration changes the velocity and the angle at which the light passes through the solution. So that's what's helping us to, or not helping us, but that's where our value is coming from. So light passes slower through a solution than in air. It moves more slowly through an increased concentration. So your takeaway on the refractometer is that it's done with a prism. Okay. It is measured against air, and about the concentration of the liquid that's in it. Okay. Now, we don't perform QC on a refractometer. However, we do calibrate it. How we calibrate is we take water and we make sure that the specific gravity is 1.000. So water should always be that. And if you're calibrating your refractometer and you're not getting that as the answer with your DI water, then you got a problem and you're going to have to figure out what's up with it. Saline is a lot higher, but we don't use it. We just use the water. You can use other commercial products, but we don't do that. And most of the time when you work somewhere in a lab, they're just going to use water as well. Oops, sorry, I didn't mean to move forward. Sorry. Okay, so a chemical strip, we'll talk more about the reagent strips in the next section when we talk about different types of chemical reactions. But with your indirect chemical strip, it also will do specific gravity. When you're having problems with your chemistry strips, like if your value is too high or too low, that's when you'll go to the refractometer. Okay. Now, the chemical strips are also measuring the ionic concentration. Now, if you have non-ionizable substances, then they're not going to be measured. And those are things like glucose, proteins, dyes. A pH change, it can be a pH change can affect it, as can an acid-base indicator. And just so you know your molecular size, it's not going to interfere. Remember when we talk about specific gravity, and osmolality, which we'll talk about in just a minute too. That has to do with sizes of your particles. Your molecular size doesn't interfere with anything on your chem strip. But it can decrease in an alkaline pH urine. So pH does cause, can cause it to be different. I still didn't mean to go forward. I'm sorry. In a comparison of the chemistry strip versus refractometer, these differ because the difference are with the density of dissolved chemicals and the number and the size of particles. So depending which method you're using will depend on which one of those is affected. Your reagent strips, they're going to change based on ions, based on the ions. They're not going to be affected by the size, remember. And then your refractometer is going to measure the refractive index. And because of that, size does matter. So any type of a large molecule you have has to be corrected for. And those were the things like glucose and protein. Osmolality, we've studied osmolality quite a bit in chemistry. So the other two are kind of new to you, but osmolality should not be. Osmolality has to do with the number of solute particles, not size, but the number of them. And the most common method is going to be freezing point depression. In freezing point depression, the values are going to be proportional to the amount of dissolved substances, okay, because we're just talking about numbers in osmolality. When we run these type of tests, you have to do a serum and a urine together, and you do that to get a renal tubular concentration. So that's what gives you your better result. Now we can move on to odor. Sorry, I forgot I didn't have another slide after that other one. So odor is seldomly significant, and it's not something that we document on a urinalysis report. However, sometimes different smells can mean something to us, and just because we don't report them doesn't mean that they're not important. And Table 5.5 actually shows you some possible causes of urine odor. But when you have either aromatic or ammonia type smells, those are both common in urines. If you have a really fresh one, then it's going to be aromatic. Whereas if you have really old ones, then they're going to smell a little bit more like ammonia. It's going to have a really strong scent. If you have anything that's that foul, putrid smell, that's with bacteria. So you've got the bacteria growing and it's going to give you a nasty smell. There's a disease called maple syrup disease, and anyone who has that disease will always have a fruity odor to their urine. And if there's anything that smells chemical related, then it's contaminated. So that's another thing that we'll have to test for when we talk about interferences on the chemical strips, is about things that can cause a contamination and give you an affect different areas of what we're testing for. So anyway, we are done with this. Like I said, this chapter was very small. And then there's a lot more in depth when we go into the chemical analysis because, you know, everybody loves methodology. But anyway,